The Hammel VB950DK is a highly efficient primary shredder designed for diverse material processing in recycling operations, including car shredding. It features two slow-moving interlocking shafts equipped with hooks and knives, rotating at a maximum speed of 43 revolutions per minute. The machine is powered by a Caterpillar C18 diesel engine, providing around 760 horsepower. With a working width of approximately 1,800 millimeters and a working length of about 2,500 millimeters, the machine has a weight of 44,000 kilograms. It is capable of handling various materials, such as wood, green waste, and car bodies, with throughput capacity depending on the type and size of the material. The VB950DK includes a discharge conveyor with a width of 1,400 millimeters and a hydraulically adjustable height for flexible material discharge. Its hydraulic system is advanced, offering automatic shaft reversal to prevent blockages during high loads. Designed with mobility in mind, it has a tracked undercarriage, ensuring easy movement within recycling facilities. Additionally, the machine can be equipped with an overband magnet to remove ferrous metals and a water sprinkler system to suppress dust. These features, combined with its robust performance, make the Hammel VB950DK ideal for demanding recycling tasks. For further technical details and operational guidelines, users can consult official resources from Hammel Recycling Technique.
At Timken Steel's mill, the large bar forged rolled process is a manufacturing technique used to produce high-quality steel bars from scrap steel. The process involves melting the scrap steel in an electric arc furnace and then refining it in a ladle furnace, where the chemical composition and temperature are carefully controlled to produce the desired steel grade. Once the steel has been refined, it is cast into large ingots of various sizes, depending on the final requirements. The ingots are then reheated in a soaking pit to a consistent temperature, ready for the forged rolled process. The forged rolled process involves using a large hydraulic press to apply pressure to the ingot uniformly, compressing the hot metal, improving its center soundness. The process incorporates multiple forging passes to enhance the ingot strength and soundness, resulting in a stronger, more uniform steel bar. The semi-finished product is then transferred to a rolling mill, where it is further processed to improve shape and size control. The rolling process delivers consistent foot weight and size tolerances, ensuring the final product meets the required specifications. The large bar forged rolled process is a tailored engineered solution that meets specific requirements for demanding applications. Timken Steel's investments in heating, forging, and inspection strengthen their ability to engineer clean steel with a sound center in larger bar sizes. Automatic loading table only for 6 m long round bar. Infinitely variable blade speed controlled by inverter. Power-driven wire brush. Accurate length index device, drive by servomotor and ball screw. Hydraulic sorting chute. Scraper, chain-type chip conveyor. We're at the factory of Anhui Green Energy in China to explore the manufacturing process of high-pressure cylinder from steel seamless pipe. The steel pipe is fed into the cutter and cut into small pieces suitable for the size of the gas cylinder to be produced. The pipe sections after being cut will follow the chain to the next step, where one end of the pipe is put into a furnace heated at a temperature of about 150 to 600 depending on the thickness of the pipe wall. The heated end of the tube then undergoes a hot spinning process to form the bottom of the cylinder. Then the cylinder is placed in a device that spins it at 1000 revolutions per minute as a torch maintains the temperature. The machine shapes the edges of the searing hot metal into a curve. In this way, the machine gradually closes off the top end and shapes two rounded areas called the shoulder and neck. Making these areas curved is the best way to contain pressurized gases. Curves spread out the stress on the middle. The sharp corner would focus. The stress in one spot, the only exit for gases will be through a valve at the top. After that, the gas cylinders will undergo heat treatment. This is the process of heating metal without letting it reach its molten or melting stage and then cooling the metal in a controlled way to select desired mechanical properties. These transitions between hot and cold, a process called tempering, strengthen the metal and make it somewhat flexible. The gas cylinder neck, after being formed, often has excess parts. They will be cut at this step. Then they go through the polishing machine. After going through the heating process many times, the gas cylinder has a lot of dirt on the outside. The gas cylinders need to be run through the polishing machine to remove the layers of dirt and polish the outside. The procedure is the same for the long gas cylinder. In this step, the gas cylinder neck will be threaded to install the locking valve system. Then drill holes for air to flow from the tank out through the valve system that will be installed later. Testing is a critical step in the production process of high-pressure cylinders. It ensures that the cylinder meets the required safety and performance standards before it is released for use. The ultrasonic testing involves using high-frequency sound waves to detect any internal defects or cracks in the cylinder. Hydrostatic testing. This test involves filling the cylinder with water and pressurizing it to a level that exceeds the maximum allowable working pressure of the cylinder. The cylinder is then inspected for any leaks or defects that may have developed during the manufacturing process. A hydraulic press indents the shoulder of the cylinder with legally required markings, such as the manufacturing date and the serial number. Before painting, the cylinder's surface must be properly cleaned and prepared to ensure good paint adhesion. This involves removing any contaminants, such as dirt, oil, or rust, using solvents, abrasives, or other methods. Once the surface is clean and dry, a primer is applied to the cylinder's surface. The primer helps to promote adhesion between the surface and the paint and provides an additional layer of protection against corrosion. After the primer has dried, the paint is applied to the cylinder's surface. The paint used for high-pressure cylinders is typically a high-quality, durable, and corrosion-resistant coating.
Bet Spring Manufacturing specializes in cold wound and hot wound coil springs for various industries, including automotive and agriculture. Their cold winding process uses high-tensile chrome silicon materials, offering lightweight springs with increased deflection for smaller applications. Hot wound springs are made using an energy-efficient furnace with bars heated to 1,750 degrees Fahrenheit before being coiled, quenched, and tempered. BETS ensures quality, on-time delivery, and continuous improvement to meet customer needs. The 24-inch pipe mill with Yoder cage forming technology is designed for efficient production of high-quality pipes, capable of manufacturing pipes with diameters ranging from 8 inches, 203 mm, to 24 inches, 610 mm, and wall thicknesses from 1 mm to 12 mm. The process begins with steel coils that are 300 mm to 500 mm wide and 3 mm to 10 mm thick. These coils undergo a thorough inspection, cleaning, and preparation before entering the forming stage. In the Yoder cage forming system, multiple small rollers, known as cage rolls, gradually shape the steel into a pipe form. This continuous process is followed by electric resistance welding, ERW, where the edges of the steel are welded together to create a seamless pipe. The system is designed to minimize material distortion, enhancing the pipe's strength and overall quality. After welding, the pipe is cut into sections typically measuring between 6 meters to 12 meters, and each section undergoes quality checks to ensure it meets specifications for straightness, dimensions, and weld integrity. Additionally, the surface may be treated with anti-corrosion coatings. The mill operates at speeds ranging from 30 meters per minute for smaller pipes to 60 meters per minute for larger ones, ensuring high production efficiency. The 24-inch pipe mill offers excellent precision and durability, adhering to industry standards and meeting the needs of various industrial applications while minimizing energy consumption. Blade machining by Sandvik Coromant involves advanced techniques to manufacture turbine blades with precision and efficiency. The process begins with the selection of high-performance alloys, such as Inconel 718, known for their strength and heat resistance. Rough machining utilizes Coromil 600 cutters, ensuring efficient material removal while minimizing tool wear through a roll-in cut method. Finish machining is done with Coromil 390 cutters to achieve the required surface finish and dimensional accuracy. Precision coolant systems are employed to enhance tool life and surface quality by effectively dissipating heat and removing chips. Finally, quality assurance is conducted using coordinate measuring machines, CMM, to ensure compliance with stringent industry standards, ensuring optimal blade performance. The fast trapezoidal roll forming line, 50 mt per minute, is a high-efficiency machine designed for producing trapezoidal sheets widely used in construction and roofing. This system ensures a production speed of up to 50 meters per minute, making it ideal for large-scale manufacturing. The machine works with materials such as CRC, galvanized steel, and painted sheets, with a thickness range from 0.40 mm to 2.00 mm. It can handle sheet lengths between 800 mm to 12 meters, catering to a variety of applications. The machine's components include an entry coil trolley, a roll-forming unit, a flying shear, and an automatic stacking system, all designed to maintain high precision and reduce downtime. Additionally, it can process up to 5 tons of material, ensuring continuous, high-volume production. The production of steel wire ropes involves several technical steps to ensure high durability and quality. The process begins with selecting steel materials, typically with diameters around 3.0 millimeters or 8.0 millimeters. The wires undergo cleaning and length adjustment before being drawn through dies to reduce diameter. The steel is then annealed in a furnace to regain flexibility. Afterward, the wires are twisted or braided into strands like 6x19 plus FC or 7x19. The ropes are coated for corrosion resistance and tested for strength. Finally, the finished ropes are wound into coils, weighing up to 5 tons and ready for shipment. A Tessie's blanking and cupping press efficiently processes metal strips into cups. It operates at 80 strokes per minute, with a 100-ton capacity, and requires a 20 kilowatts power supply. The machine's size is 2,350 millimeters W, 2,800 millimeters D, and 3,870 millimeters H, with a total weight of 13,500 kilograms. The biaxial rotor blade testing process involves simulating realistic operational loads on wind turbine blades. Using fiberglass springs and decoupled masses, the system is tuned for eigenfrequencies. Testing combines flapwise and edgewise loads to mimic actual wind conditions, with forces reaching up to 10,000 N. The process ensures blades withstand 20 years of operation, with results guiding design optimizations. Data from sensors are used for refining materials and improving blade performance over time. Bruck, located in Saarbrücken, Germany, specializes in the production of seamless hot-rolled rings, flanges, and custom-forged parts. Their seamless rings range from 300 mm to 6,400 mm in diameter and can reach heights of up to 1,600 mm, with radial widths up to 1,000 mm and piece weights up to 40 tons. The company also manufactures forged parts with dimensions up to 4,500 mm by 4,500 mm by 10,000 mm, and piece weights up to 50 tons. Bruck GmbH works with over 1,000 different material grades, including carbon steels, stainless steels, nickel alloys, aluminum, and titanium. They offer services such as heat treatment, machining, welding, and assembly for clients in sectors like chemical, petrochemical, and power industries. Mechanica Zella, ISO 9001 certified, has been a leader in precision mechanics since 1969, specializing in turning and boring works for medium to large components. Equipped with CNC machines, their boring capacity reaches 3,500 mm by 1,200 mm by 2,000 mm, while their turning capabilities accommodate shafts up to 1,450 mm in diameter and 6 meters in length. The company uses CAD/CAM 3D systems for precise production cycles, ensuring top-notch quality through ultrasonic and magnetic particle testing, dye-penetrant inspections, and heat treatments. They serve industries like energy, iron and steel, petrochemicals, and plant engineering. The intense labor at Saarschmied GmbH in Völklingen, forging 80-ton generator shafts for power plants and ships. Molten steel, heated above 1,700 degrees Celsius in an electric furnace, is poured into molds, cooled, and reheated in a massive oven consuming as much gas as a small town. In the world's most advanced open-die forge, a hydraulic press shapes the glowing ingot. Through stretching and upsetting, the steel structure is densified, with slag blown off and cracks burned out using oxygen. Crane operators and smiths carefully maneuver giant grippers to prevent million-euro damages, using chains and manipulators to handle the colossal workpiece. After multiple heating and pressing cycles, the shaft is hardened in a water bath. Precision machining removes up to 14 centimeters of steel, achieving accuracy within half a millimeter. Producing over 200 shafts annually, Saarschmied blends high-tech precision with backbreaking effort, with each shaft valued at around 200,000 euros. The process begins with a pinion fixed to the machine's spindle. Hesap's automated tool precisely cuts or grinds the gear teeth, following the paloid tooth shape for smooth power transmission. The CM tire recycling crumb rubber system turns tires into useful materials in 4 stages. Stage 1, the CM primary crusher crushes the tires into crumbs. Stage 2, the primary crusher removes the steel, separates the fibers, and creates clean crumb rubber. Stage 3, the granulator processes the crumbs into 4 mm rubber granules, screens them, and extracts the fibers. Stage 4, the dual drive mill grinds the granules into a fine powder of 10 to 80 mesh. The powdered rubber is used as landscape mulch, playgrounds, TDF fuel, or TDA aggregate. The H-beam steel construction process begins with cutting the steel to size. The panels are assembled and welded using submerged arc welding, S-arc welding. The beam undergoes non-destructive testing, NDT, including visual, ultrasonic, magnetic, and verification. Welders and high-level installers perform the welding and installation. Finally, the beam is protected by paint. Stator and rotor generator repair at the Farmington facility uses FAR, OAR, MTM gauges. The process includes full or partial rotor assembly, ring manufacturer and tool holder, stator repair, and rebuild. Stator rods are manufactured in Poland, ensuring high quality. Pink parts are precision machined, high-speed balanced to 50 tons at 4,150 revolutions per minute, NDE Level 2 non-destructive testing. The ISO-certified facility, with 3 clean rooms, provides independent problem-solving engineering, ensuring optimal generator performance and superior reliability. Spirit AeroSystems manufactures the forward fuselage, engine mounts, fixed leading edges, and moving leading edges of the Boeing 787 wings. The Wichita process includes precision metal cutting, frame assembly, component mounting, and quality control. State-of-the-art machinery and skilled workers work together to ensure high precision. The video highlights Spirit's advanced technology and efficiency in delivering critical components to the aviation industry. The aluminium smelting process at Kitimat uses the Hall-Héroult process, refining bauxite into alumina, which is then melted in an electrolytic cell with coke and a carbon anode. The molten aluminium is drawn off and cast into ingots or billets, ensuring high quality. The Uniflex UBM 6-20M tube bender is a low-cost, yet efficient manual solution for bending metal tubes. With a sturdy frame and hexagonal support, the machine can be easily fixed on a vise. The UBM 6-20 accurately bends tubes with a diameter of 6 to 20 millimeters and a wall thickness of up to 2.5 millimeters. The telescopic handle and multiple adjustment options allow thick tubes to be bent without distortion or waviness, ensuring high quality, suitable for applications requiring precision and durability. ABB's Azipod propulsion system improves safety, performance, reduces fuel and environmental impact for ships globally. The steelmaking process begins with recycled steel scrap, which is sorted, stored, and fed into the electric arc furnace along with sponge iron. The iron ore is processed using direct reduction technology, using natural gas at 1000 degrees Celsius, converting it into almost pure sponge iron, significantly reducing CO2 emissions. In the electric arc furnace, sponge iron and scrap are melted by electric current through graphite electrodes, reaching temperatures of 1600 to 1630 degrees Celsius. The molten steel is automatically sampled to ensure quality. The steel is then poured into a continuous casting system through water-cooled copper molds, forming billets up to 16 meters long and weighing 2 tons. The billets are cooled, cut with oscillating scissors, reaching temperatures of 950 to 1100 degrees Celsius. The billets are further heated above 1000 degrees Celsius, then hot rolled through multiple stations, gradually reducing the size to steel wire, with a diameter of 5.5 to 16 millimeters. The wire is coiled into rings at speeds of up to 100 meters per second, cooled in a controlled manner on a conveyor belt to shape the mechanical properties. Finally, the rings are pressed into 1.5-ton bundles, tied tightly and automatically labeled with detailed information, ensuring high precision and quality. If you want to visit Georg's Marienhut GmbH, you will have to go there. Long steel is smelted in electric arc furnaces, processed through graded treatment, and continuously cast into strength. The steel can be heated into bars, ensuring precise diameters. Steel samples are analyzed regularly, meeting the needs of cars and machinery. Hydraulic cylinders are manufactured in Rissa, Norway, using state-of-the-art Mazak Integrex machines, combining CNC turning and machining. Submerged arc welding ensures quality. Simulation X tools support design. Accurate virtual testing. Cylinders withstand harsh conditions, meeting strict marine standards. CNC dry cutting of bevel gears, achieving high precision. Optimal efficiency, no coolant required. The full scrap metal recycling plant features an advanced and integrated process for efficient metal recycling. The system starts with a 4T capacity mobile vibratory charging machine, which feeds scrap metal into the furnace for melting. The vibratory mechanism ensures uniform material distribution, optimizing the furnace operation. Once the scrap is charged, it enters a 15 TTR12 tilt rotary furnace equipped with oxy-fuel firing technology. This system enhances combustion efficiency, providing high heat output to efficiently melt the metal, ensuring minimal energy consumption during the process. After the metal is melted, it is transferred to a 15T lip axis side-tilting holding furnace that includes a porous plug gas injection feature. This allows precise gas flow control to maintain the molten metal's quality and temperature, minimizing oxidation and improving uniformity. Next, the molten metal is cast into ingots, using a 220 mold ingot casting machine, which utilizes indirect water cooling to ensure rapid and uniform solidification. The machine's cooling system ensures the ingots maintain the correct temperature and quality. Following casting, a robotic ingot stacking line is used to organize the ingots, which are then subjected to a cooling quench process for controlled cooling and safe handling. Finally, the plant features air pollution control systems with continuous emission monitoring to track and minimize environmental impact throughout the recycling process. This plant is designed to be both efficient and environmentally compliant. The Andritz hydro-pumped storage plant in Langen-Prosselton, Germany, plays a critical role in energy supply, operating at 16.7 Hz, with a production capacity of 250 tons of crude steel. The plant utilizes centrifugal forces of 27,000 tons at each pole, with 12 axes measuring 26 meters. The system spans an area equivalent to 14 soccer fields, using steel sheets totaling 144,000. This facility supports 10% of Deutsche Bahn's energy needs, highlighting its significant role in energy storage and distribution. Pima Welding Automation provides advanced robotic welding systems designed for heavy industries. Their robotic welding stations can handle parts up to 15 meters in length and thicknesses ranging from 5 millimeters to 100 millimeters. The company's welding positioners allow 360-degree rotation, enabling precise welding of large structures. Their column and boom welding systems feature booms that extend up to 16 meters. Skilled technicians program and monitor the systems, ensuring quality control with real-time performance tracking. These systems are employed in industries such as shipbuilding, wind energy, and power generation to improve efficiency and welding quality. At GM's Fort Wayne Assembly Paint Shop, the process starts when welded truck bodies enter from the body shop. The bodies are cleaned, rinsed, and immersed in a zirconium pre-treatment bath to prepare the surface. After the E-coat primer is applied, the truck enters the first bake process to ensure durability and corrosion protection. Robots seal seams for waterproofing, and liquid-applied sound deadener is used for a quieter ride. Trucks are inspected manually after each stage. The trucks then receive anti-chip coating and primer before entering a second bake. The final paint is applied in 10 paint modules, followed by a final inspection to ensure a defect-free finish. This process produces over 1,300 light-duty pickups daily, ensuring durability and a high-quality paint finish. The 13,000-ton hydraulic forging press is a key industrial machine used to shape large metal parts with high precision. It operates with a maximum press force of 13,000 tons, 130,000 kilonewtons, and a stroke of up to 500 millimeter. The machine's main hydraulic cylinder ensures efficient forging, while its 60 kilowatts motor powers the entire system. The press's maximum opening height is 1,400 millimeters, allowing for the processing of large components. The production process begins with preparing the raw material, which includes heating the steel billets to 1,100 to 1,200 degrees Celsius for 2 to 3 hours. These heated billets are then shaped under immense pressure, achieving a final product size ranging from 200 millimeters to 500 millimeters in diameter. After forging, the parts undergo machining, heat treatment, and surface finishing to ensure quality. The parts are then carefully inspected for precision before being packed and shipped using specialized equipment.